If your search stack feels random, you may be fixing ranking when recall is the real bottleneck. I'll build candidate generation plus re-ranking in Python and show where relevance really breaks. This is the setup you'll be able to run after this, which builds a recall pool and then re-ranks it to return the best docs. I'm Professor Pi, teaching AI foundations with simple Python. Search systems often fail in one of two ways. Either the system never sees the right document, or it sees it but ranks it badly. Candidate generation plus re-ranking separates these concerns so you can measure them independently. In practice, this means a fast generator fetches a recall pool, and an expensive re-ranker sorts that pool using deeper models. That split helps you trade latency against accuracy in a principled way. At a high level, candidate generation finds a short list of potentially relevant documents. Re-ranking takes that short list and scores each pair with stronger context awareness. Think of the generator like a scanner that opens the door to a room of possibilities, and the re-ranker like an expert who inspects each item in the room carefully. Success looks like high generator recall and a re-ranker that reliably promotes the truly relevant items to the top. We will build a tiny toy pipeline that reveals when recall limits your end result. The code uses simple embeddings for the toy part, then demonstrates a FAISS generator with a sentence transformers encoder, and finally, a CrossEncoder re-ranker for precision. The point is to show which stage is failing, not to deploy a production system. Now we will start with a minimal retriever to expose the basic failure mode. Now we will run a toy retriever to see how top 1 can be wrong, while recall is okay. This snippet simulates a bare-bones retriever to expose when recall and ranking get confused. The list docs holds 4 tiny documents, and Q is a short query. The arrays DV and QV act as toy embeddings. A dot product approximates similarity without any external model. The vector order sorts documents by score. Then rank finds where the known relevant document, index 0, lands in that sorted list. Finally, top 1 grabs the highest scoring document to show what a naive system would return. If you tweak values inside DV, you will move the relevant document up or down. The printed rank shows recall is fine, but the top 1 ranking is wrong. Next, we will build a FAISS-powered candidate generator with an encoder. This example builds a FAISS candidate generator powered by a sentence transformers encoder. The sentence transformer object, enc, turns docs into normalized vectors, which are added to a FAISS index/IP for efficient inner product search. The query, Q, is encoded into QX the same way, and IX search returns top candidates with their IDs, I. The list cans maps result IDs back to document texts, producing an interpretable candidate set. Raising the search size from 3 increases the chance of catching relevant items, but also consumes more downstream re-ranking budget. The printed list shows which documents FAISS can recall before any re-ranking happens. Now we will measure generator recall across a few queries. This code measures generator recall by computing a top K hit rate with FAISS. The list QS holds 2 queries, while gold provides the index of 1 relevant document for each query. The encoder ENC creates normalized vectors for QS. Then IX search retrieves the top 3 candidate IDs for each. The variable hits counts how many queries had their gold document appear in the returned IDs, and HR normalizes it to a rate. Increasing K generally boosts hit rate, but also grows the amount of work handed to re-ranking. The printed hit rate isolates the candidate generator's quality without conflating re-ranker behavior. Next, we will re-rank the candidates with a CrossEncoder for stronger scoring. This snippet re-ranks FAISS candidates using a sentence transformer's CrossEncoder. The CrossEncoder object CE scores query document pairs directly, modeling rich interactions that by-encoder retrieval cannot capture. We first pull top 5 candidates with ix.search, form pairs between Q and each candidate in cans, and call CE predict to get scores. The list order sorts candidates by these CrossEncoder scores, and top selects the best text while S records its confidence. Increasing the candidate list from 5 can improve precision, but adds latency because CE.predict is expensive. The printed top 1 shows which candidate the re-ranker prefers and how strongly. Now we will compare 2 different candidate budgets to see which stage is the bottleneck. This example contrasts 2-stage behavior under different candidate budgets. The FAISS generator retrieves K1 and K2 candidates, producing 2 candidate sets, C1 and C2. The CrossEncoder CE then scores each set, yielding re-ranked top 1 results T1 and T2. The booleans H1 and H2 indicate whether the known relevant document, index 0, appeared among generator outputs at each K. If K increases, generator recall often improves, H2 may turn true, and the re-ranker gains options, possibly changing the final top 1. The printed values make it clear whether a recall shortfall or re-ranking choice drives the observed outcome. This toy flow maps directly to a real-world checklist. If the generator never returns the gold document, improve embeddings, add more candidates, or use an approximate nearest neighbor index with tuned probes. If the generator has the gold item, but the re-ranker does not promote it, consider a stronger CrossEncoder, more training data, or features that expose relevant signals. Recap: candidate generation finds a recall pool quickly. Re-ranking inspects the pool deeply to pick the best result. Caveat: a tiny pool hides generator failures, and an expensive re-ranker cannot fix missing items. Next step: try increasing the FAISS candidate budget and measure hit rate and re-ranker latency while keeping the re-ranker model fixed. If you need guidance on tuning, run the same experiment with different K values and collect timing and hit rate. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.